Hi everybody, welcome to the fourth of our Destination Space events. Welcome to Space Rocks, Meteorites and Asteroids. My name is Helena and I am an outreach officer at the Department of Physics and I'm hosting all of these events. It gives me great pleasure now to introduce our speaker for today. So we have with us Dr. Helena Bates. Now Helena completed her DPhil at Oxford, joint with the Natural History Museum in London, and she has spent her time looking at space rocks. And is now the interim meteorite curator at the museum and is responsible for looking after over 5,000 meteorites, among many other duties, I am sure. Without further ado, I will hand over to Helena. So thank you very much.
Thank you. Right, I'm going to share my screen. So as Helena mentioned, my name is Helena as well, and I'm the interim meteorite curator at the Natural History Museum in London. But I did just finish my PhD, my DPhil, working in the Space Instrumentation Group in Oxford with Tris and Catherine, if you might have seen some of their talks in the previous weeks. And so I'm today going to be talking to you about space rocks. Everybody loves space rocks, but what they don't quite realize is how broad that term is and what that might encompass. And in fact, most things in space, unless they're like a gas or anything like that, are actually space rocks. So it's quite a broad term. So I thought to start off with, I was going to help define what an asteroid and what a meteorite is, because you might have heard these terms a lot thrown around. You might have heard of meteors as well. They're often a term that you might have heard as well. But what actually is the difference and what are these terms? Because we really like naming things. So to start off with, right at the beginning, an asteroid. An asteroid is essentially a rocky body that orbits the sun. So I've got here a picture, sort of a little schematic of the solar system. And you've got the inner terrestrial planets here, and then you've got Jupiter. So it doesn't quite go out to all of the outer planets. But you have all these like little dots here, and some of them extend quite far out. Some of them are actually even in Jupiter's orbit, and some of them extend down actually quite close to Earth. These are asteroids. So these are the building blocks essentially of planets. And we think that they're actually leftover rocky material from the beginning of the solar system. So they're super duper old, and they're actually really primitive. So primitive is a term we use to basically mean very pristine, very precious, things like that. So we call this kind of concentration of asteroids in this region here the asteroid belt. So I've got a little animation you can see. The main definition, the main thing you need to remember about asteroids is they orbit the sun. So these are things that are in orbit, like Earth, in our solar system around the sun. So at the beginning of the solar system, this asteroid belt was really quite chaotic. And lots of bits would knock into each other. Dust would be thrown off asteroids, chunks, things like that would be knocked off as well. So my little cartoon here just shows that sometimes larger bits can get knocked off asteroids when things knock into each other. Now, this little chunk of asteroid here is sometimes called a meteoroid. Now, don't worry about that term. It's really not used very commonly at all. But I thought I'd just mention it in case anybody asked, or you might have heard that term before. But this little chunk of rock gets set off on a new path. So the asteroid is orbiting the sun, but this little chunk basically gets thrown into some other orbit. And if it's lucky or potentially unlucky enough, that chunk of rock will intersect with where Earth is. It will intersect Earth's orbit and it will enter Earth's atmosphere. So when bits of rock enter Earth's atmosphere, they burn up. And if they're small enough, they will be completely destroyed by their journey through Earth's atmosphere. So essentially, friction with air molecules will cause these really bright trails. And these are called meteors. So you might have seen meteors, you might have seen shooting stars. It's the same term here. And actually, we have sort of periods in the year where shooting stars are more likely to be observed. But pretty much, if you're looking up at the sky at night, on a clear night, and you sort of stare in one location for long enough, you may well see really fast like bright sort of streak of light, and that is a meteor or a shooting star. Now, sometimes these chunks of rock that came from the asteroid are quite a bit larger. So we're thinking maybe house-sized or bus-sized, something like that. If those enter the atmosphere, then they burn up, but they actually survive. So they're not completely destroyed by that really hellish journey, and they can land on the ground. To create something like a crater, like a much larger impact, something that we were talking about last week, the Arizona crater, the Barringer crater in Arizona, you need something very large. And so don't worry about that. We're not going to be talking about anything that's going to be causing any sort of damage or anything. We're talking about these rocks that kind of fall quite gently to the surface of the Earth. And at that point, at the point that they hit the ground, that's when they become a meteorite. So these are rocks from space that we can pick up and study. And we have NASA, the American Space Agency, actually sends scientists to Antarctica to pick up meteorites every year. I don't know if they went in 2020, I'm not sure. But they go every year to look for meteorites, and they go to Antarctica, not because it's where most meteorites fall, but because, for the simple reason that it's a white background and the rocks are very, very dark. So that's basically the difference between an asteroid and a meteorite. That's the kind of, if you're going to take away anything, that's a really good thing to remember. But I want to go into a little bit more detail about what different types of meteorites we have. So we have to go back to the asteroids themselves. And it turns out asteroids, they vary in sort of shape, size, what they're made of, what they look like, things like that. But they can broadly be summarized into 3 different types, asteroids in our solar system. The first type of asteroid is quite rare, but it's really, really big. And when it's really, really big, there's lots and lots of heat on the inside of this asteroid, and that causes this splitting into layers. And so you see this little cartoon here, we have a central area, which is probably like a metallic core. Then you have a mantle and you have a crust. So you might have heard those terms, core, mantle, and crust, when talking about the Earth. And this is very similar. There are some asteroids out there in space which have the same sort of internal structure as Earth, but probably on a much, much smaller scale. So they're not quite as large. But most asteroids that are kind of out there never really got large enough to have actual melting on their inside, to have the splitting into layers. So they probably just sort of sat and were heated. So that's what this image indicates. It's hot on the inside, but it's not that warm. And then you have these asteroids, and these asteroids are my favorite. And so I'm not at all biased, but these are what we call primitive asteroids. And these asteroids are basically very small, and they just represent like really like almost like dust bunny-like consistency of material that formed, that accreted together, that stuck together right at the beginning of the solar system. And nothing has happened to these things since for billions and billions of years. So these are ways for us to look back in time at the beginning of the solar system, these really primitive ancient meteorites. And we have meteorites, really primitive asteroids. Sorry, see, even I get confused between the different terms. So we have different types of meteorites from these different types of asteroids. And they're quite easy to tell apart. So we're going to start by looking at the meteorites that come from these really, really large asteroids. And what's really unique about these is there's nothing like this that's naturally occurring on the surface of the Earth. So we have here what's called an iron meteorite, which we think comes from the core of this really large asteroid. You can't get naturally occurring pure iron on the surface of the Earth. If you find pure iron, it's probably a byproduct of, we get all our iron from mining and things like that, processed rocks. But this is naturally occurring, and that's not normal on the Earth's surface. But what's really cool about these iron meteorites is they have this beautiful crisscross pattern. I don't know if you can see in this image, but I'll show some more later. This crisscross pattern, these are basically metallic crystals. So crystals in rock grow when things cool slowly. And so what the presence of these crystals suggests is that this meteorite, this rock, was kept warm for a really long time. Alternatively, it was inside a planet. That's a nice way of thinking about it. We also have, we call these iron meteorites. Very originally, we called these meteorites stony iron meteorites because essentially they're mixes of stony material and iron material. And we think that they come from the point at which you have your metallic core touching your rocky mantle, and you get this like beautiful mix of material. You get these amazing crystals of kind of rocky material, and then this like matrix of metal. Very unusual looking rocks, very easy to identify if somebody has one of these, but they are quite rare. And then we get to the meteorites that come from these heated asteroids. These are a little bit more difficult for us to identify as meteorites because they might have been, they've been processed a bit, they're heated, but essentially they are super duper old, and they are super duper precious because all that's happened to them since the beginning of time or beginning of the solar system is they've just been heated gently. And And then my favorite, we have the primitive meteorites. But like I said, the primitive asteroids, they're very, very delicate. You know, they're friable. You look at them and they fall apart. That's all it takes. So we have to be very careful with these asteroids, with these meteorites. So this here is an example of a primitive meteorite. This meteorite is called Evuna. We have it in the meteorite collection at the museum, and it's kept in a special atmosphere. But what you can see in this meteorite is it's really, really, really dark. Really, really, really dark. Which it's unusual. And Evuna is a special case. But these things, if I held this rock, it would just fall apart in my hands, which is pretty awesome. So now I'm going to show you a video that I took in the meteorite collection when I was there. So I was lucky enough to go into the museum on Monday. It's currently closed to the public, but I was able to go in and well, do my work. But I also managed to take a video for you guys. But yeah, so hopefully this this brief introduction to meteorites will help you with the video that I'm about to show you. And then afterwards, we'll talk a little bit more about other types of space rocks. So let's have a go.
So welcome to the inside of the Natural History Museum meteorite collection. Obviously, this is going to have to be how we show some of our specimens. If we were in person, we would be able to do some handling. But actually, one of the advantages of being online is I can get out some of our larger specimens, and you can see some of the larger things that we have in the collection here at the museum, which I wouldn't be able to carry if we were doing this in person. So that's quite exciting. So I've got out here a selection of different types of meteorites, and we're going to have a little look through all of them. So hopefully I've told you about how different meteorites come from different asteroid types. And we'll start with having a look at the meteorites that come from the core of really big asteroids. And so here we have an example of an iron meteorite. So these are handling specimens. Normally we don't touch these with our hands because our hands have oils and things on them, which can affect some of the samples. But because these are handling specimens, that's okay. So this here is an iron meteorite. We've sliced, it was actually a much larger piece, and we've done a slice of it. And you can see it has that crisscross pattern on it. It's really, really beautiful. And these, like I said, are metal crystals, which basically suggest that this was hot for a really, really, really long time. So we think that this came from the inside of a really large asteroid. Unfortunately, most iron meteorites don't look like this. They actually look quite a lot like this. So this is an example of an iron meteorite as well. So it's magnetic, but it's very, very heavy. But you can see it's all orange on it. And this is basically rust. So this has been sitting in the desert for a really long time, and this is one of the disadvantages of or one of the difficult things we have to work with when we're looking at meteorites. So it's a bit of a shame. It's a beautiful specimen anyway, really weird shape, but that's probably just because it's been sort of knocked and stuff around like that while on Earth. So these are the two types of iron meteorites that I got. We also have much larger iron meteorites. So for example, this thing here is a piece of one giant iron meteorite, and I'm not going to touch this because this has got some stuff on the outside in an attempt to try and preserve it. But this is one whole large iron piece, and they actually do get much larger than this. The largest iron meteorite we have in the collection is 3 tons, but that's on display. And you can also see here another of these slices, and you can see some arrows. This is a more old collection, or a more old piece of the collection, which is showing those amazing crisscross patterns. So those are the iron meteorites. Now we also have some stony iron meteorites. Remember, these come from the point at which you have your iron core interacting with your rocky mantle, and they look absolutely bizarre. So this is a really beautiful, really large specimen of a stony iron meteorite. Again, it's a handling specimen, so I can't touch it. But you can see you've got this metal, and then interspersed in between you have these little crystals as well. So they're beautiful. Amazing samples. They also can look a little bit like this. So here again, you see this is a massive piece as well. So these also get very large. You've got some rocky bits, and you also have some metallic parts as well. And so the final meteorites we also have are the stony meteorites. So I've got a couple of examples of some of the stony meteorites here. So this is one of them. This is a really large, beautiful piece, and you can see it's got loads of things going on inside. It's got lots of sort of circular things, and you can see some dark things, and it's all, if I sort of, well, you can't really see, but it is a really beautiful specimen. And then here we've got a slice of a similar sort of meteorite, and you can see actually there's a sort of slight iridescence to it. Possibly you can't see, it's quite difficult to tell on video, but that's actually metal inside it. So these samples come from basically those heated asteroids, so asteroids that are large but not quite large enough to have the layers splitting up inside them. So these, in conjunction, the iron meteorites, stony iron meteorites and these rocky meteorites can basically tell us what the planet looks like, which is pretty cool. But then you have something like this. So this here is an example of a meteorite from a very primitive asteroid. So this is essentially just an accumulation of the material that was there before planets existed. And you can see some of these very small white flecks in this meteorite. And these are, we can date these. And these are the oldest solids in the solar system. So when the solar system was forming, they're the first solids to have formed. So they're pretty extraordinary. So like I say, this is a handling specimen, so I can hold this. But we actually have to be very careful with our primitive meteorite specimens. And so most of the time, they're kind of kept in environments like this. So this is Ivuna, and it's held in a nitrogen environment to try and preserve it, to try and stop the terrestrial weathering. The terrestrial atmosphere causes an effect on the meteorites. And you can actually see on the surface of the sample, you can see some of those that white material. That's actually terrestrial effects. So it's a real shame sometimes when you have spent ages looking at a meteorite and seeing the terrestrial effects when all you're really interested in is the extraterrestrial effects. So yeah, that's it for my little mini tour around the meteorite collection. I hope that was interesting. And now back to the main talk. Thank you.
Okay, back to me now. I hope that was interesting. I realised I said a lot of what I said in the talk, but you know, that's also fine as well. So I'm going to really quickly, we've sort of touched on the meteorite rocks that we have, the space rocks that we have available on Earth, but there are also space rocks still in space that are interesting to us as well. And like I was mentioning in the talk, terrestrial contamination, rust, that sort of thing is a really big issue for us. And so one of the main things, one of the best solutions to that is to actually go to one of those asteroids before bits get knocked off and then pick up samples and bring them back to Earth. This isn't a new idea. No, go to the next slide. This isn't a new idea. This is something that has been done a couple of times over the past couple of decades, most notably by the Japanese space agency JAXA. And they went to an asteroid that was kind of nearby Earth and returned samples of that sample. They returned 90 milligrams of material to Earth in 2010. And they've never exposed that material to the terrestrial environment, which means that it's pristine. The only signal that we're ever going to get from it is extraterrestrial. And that mission was called Hayabusa. And following on from Hayabusa, there was because it was really successful, they decided to do a second mission, Hayabusa 2. Hayabusa 2 launched in 2014, and it went to another near-Earth asteroid, a slightly different one this time, and it brought back samples on December 6th, 2020. So really recently managed to successfully bring back 4.5 grams of material from a near-Earth asteroid. But the one I want to talk to you about really briefly, because I know we're running out of time, is OSIRISREx. So OSIRISREx is a NASA mission to an asteroid, very similar to Hayabusa 2, but I want to talk about it because Oxford has worked on some of the data analysis of this mission. So OSIRISREx is what we call a sample return mission. These are all sample return missions. It's going to go to the asteroid, bring samples back. So on the 8th of September in 2016, OSIRISREx launched from Cape Canaveral. Some people in the group in Oxford were actually lucky enough to attend the launch, which was pretty awesome. I would have loved to have gone, but it was before I joined the group. And then it went on this kind of convoluted, the rocket then went on this kind of convoluted journey to match its orbit ever so slightly to the orbit of its target asteroid. So this little animation here shows the kind of path that the spacecraft took to match up with its target asteroid. So the target asteroid is in red here. And you can see how it launched from Earth, and then it had a sort of Earth gravity assist, where it basically used the gravity of Earth to speed up. And then in October 2018, it approached this asteroid, this bizarre near-Earth asteroid, and this is a series of 12 images taken as the thing where I got closer to it. And and so it took these 12 images as it approached, but then we finally got this final image, which was taken from 15 miles above the surface. It's actually a compilation image of a bunch of different figures, but this is asteroid Bennu, and this is an asteroid. So this is basically where we think some of those really primitive meteorites that I was talking about in the talk and earlier have actually come from. So we've kind of skipped out the middleman of having to go to the mission. having to, you know, have the meteorite journey through space and then land on Earth. We're literally going straight to the asteroid. So really briefly, I just want to discuss why they chose this asteroid. And if they kind of have this really nice succinct way of saying it. Okay, so there are about 500,000 asteroids in the asteroid belt, but most of them are too far away. So we want to go to ones that are nearby Earth. So that limits the number that you can go to. Next, everything in space, basically, everything in the solar system exists along this like plane, and but slight variations from that plane will cause more difficulty for a spacecraft trying to reach. So basically, you want to have something that's on a similar plane to Earth, which is what this indicates. There's only 192. Then you want something that's big enough that, you know, if you go and collect some sample, it's not gonna it's going to be doable, basically. It's only 26. And only then could they consider the science. Only then could they basically say, okay, now we can decide which one of these are scientifically interesting. And so they picked asteroids that they think looked like these very primitive bodies. And one of the ways that they could try and identify that from the ground was to look and see if they had any carbon in them, which suggests that they have very primitive material on them. And there's only 5, in which case they eventually did. They kind of came up with Bennu at the end. So this was a sample return mission. So they had to find a place that they thought was appropriate to, oh yeah, I'm being told to wrap up quickly because I'm going really fast. Okay, so we did some sampling on Bennu. This is the sampling site that we went to. This is a really brief video of how the sampling was supposed to occur. So essentially, you've got a spacecraft descending to the surface, and then I'll just show you quickly. Descends to the surface, and then it shoots out a puff of nitrogen gas to kind of like mix up the material, and that's the idea is then when it kind of goes back up again, it will scoop up some of that material. Yeah, and that is what happened. Next. This is a GIF of the images of the spacecraft descending to the surface of Bennu. And you can see all of this material is knocked up. It looks as though it was only in contact for a very short period of time, but it was actually 6 seconds in total. And then to check whether this was a success, whether this sampling was a success, they looked at images of the sample holder after they descended, and they could see all this material kind of flying out. And actually, this was a bit of a concern because they thought, oh no, we're losing material. So they really quickly stored it in the sample return capsule. So this is the thing that's going to be delivered back to Earth in 2023. So final thing I'm going to say, what's OSIRISREx doing now? They're going to be analyzing the images that were taken during this event, this touchdown event. They're also going to be trying to work out what's going on. Bennu's doing something a little bit strange. It has these kind of seemingly at random kind of it expels some material in a kind of bit of a random way. And that's still up for debate why that's the case. And so I reckon the scientists are going to be looking at that a lot over the coming years. But then OSIRISREx is actually going to leave Bennu in 2021 and hopefully return the samples in 2023. So I will leave you with this slide basically saying that no matter where your space rocks are from, they're cool. So yeah, thank you very much. I'm finished now.
Excellent. Thank you so much, Helena. Okay, that was a really fantastic talk. So thank you for telling us so much about all these amazing space rocks. And we have lots and lots of questions. So if you want to stop sharing your slides so we can see your face a little bit better. Amazing.
Yeah, sorry for overrunning a little bit. I think I got a bit enthusiastic at the beginning.
That's fine. We like seeing people being enthusiastic about space rocks. And we can see you're all really enthusiastic in the audience as well. We've got lots of questions coming in. So let's get to some of those. So let's kick off with this one. So could an asteroid or meteorite carry life?
So this is a really, really interesting question. There's actually quite a lot of studies have been done looking at whether very primitive sort of small organisms could survive first the sort of ejection from its parent body, and then the journey through space, and then the impact on Earth. And they have found that you might have heard of the term tardigrade. These are sort of very small, microscopic, little bacteria-like things that are very, very resilient, and they have been shown to survive quite extreme environments. I'm not sure whether they would survive quite the journey and the sort of hellish experience that a meteorite might have. But what meteorites do have in them is organic material. So one of the things about Bennu, it said it had carbon in it, and that's organic material. So that's not life, but that is the building blocks of life. So you might have heard of DNA. Well, DNA is made up of amino acids, and these are like little kind of like molecules that build DNA. It's not DNA, it's not like, it's by no means life, but you also find amino acids in meteorites. So, you know, could life have been transported? Probably not, but maybe the building blocks. So, yeah.
Fantastic. That's an awesome answer. And that's part of the reason why we're so interested in studying these, right? Yeah. Space rocks can tell us a lot.
They can. They're the best.
And so with that in mind, we have another question here asking, how do you tell the difference between just a common rock and a meteorite?
That's a very good question. It's my job. It's actually quite easy. It's easier than you think. Meteorites look quite different. For example, those stony iron meteorites, the ones which have the metal like matrix and then the crystals in them, nothing like that occurs naturally on Earth, not easily. Some of them are more difficult to identify, but we have training to spot specific kind of structures and things inside them that might that we can spot, and we can be like, okay, that's definitely that. And then if we have an idea, if we're pretty reasonably certain, then we can do some actual kind of chemical analysis. So what we do is we crush a bit up and we look actually what it's made up of, and we look at the weight of we look at the weight of various elements on them, and Earth has a very specific kind of budget of material. And if you have a meteorite that comes from somewhere else in the solar system, it will have a very different specific budget of material. And so we actually look, there are ways in terms of that for identifying whether something is a meteorite or not.
Okay, so there are ways to tell the difference. Excellent. Why do they have crisscross patterns? So where do those patterns come from?
So these patterns are called, and I'm going to mispronounce this, Wittgenstein patterns. So these are unique to iron meteorites, but basically all rocks are made of crystals. And the size of your crystals depends on how long or short amount of time your rock formed in. So if it formed for a really, really long time, the crystals could grow really, really large. So because we form rocks by basically cooling things down for them solidifying. So if you have an iron meteorite that cools really, really slowly, you get these really large metallic crystals in them. But also the reason that you have slightly different colors of the crystal and why they're slightly different and why they crisscross is they have slightly different, we were talking about budget, element budget, the weight of the various elements in them, the slightly different weights of elements in each of those little crisscrossy patterns. That's basically why. So yeah, it's to do with cooling very slowly. That's the idea.
Yeah, that's all about crystal formation. Yeah.
And
that's a big topic of study for kind of earthbound crystals as well. There's a lot of research that goes into that too. Okay, I've got another question here. When a meteoroid breaks off, does that affect the orbit of the asteroid that it's broken off of?
Yeah, it will do. It will do, definitely. Depends on how big the asteroid was and how big the meteoroid was. But yeah, essentially. In fact, we think we might have, well, no, we don't. There was some debate, some discussion when OSIRISREx descended to the surface of its asteroid, whether that bump would change its orbit. They think it's probably small enough. But so it's, these things are held in these kind of like amazing configurations. Ever so slight variations will change things. So yeah, it will. Yeah, not much though.
Nice. Okay, and we've got lots of questions asking about sort of what happens when these things hit Earth. How many have hit Earth? Sort of what are the sizes of the ones that have hit Earth? I think I saw one asking, could that? What was the size of the impact crater that they make? So can you tell us more about the impacts that we've had?
Yeah. So impacts that cause craters aren't particularly common. The general rule of thumb is, the general way I think about it is, if you have a crater that's a size, the thing that caused it will be a tenth of that size. That there will be some slight variations in that, but so for example, Barringer crater, Catherine might have to correct me if I'm wrong, I think is a kilometer. Is it 10 kilometers? So okay, so it's 1 kilometer in diameter. So probably the thing that caused the impact was 100 meters. So it's a tenth of the size. That's the general rule of thumb. In terms of things hitting the Earth, the number that we quote is there is 40,000 tons of material that hit the Earth's atmosphere every year. Most of it is dust, but some of it will be large enough to create meteorites. We think over a plot of land of the size of the UK, there are probably about 10 meteorite events a year. So, but whether we see it or, you know, most of the Earth is water, right? Like it's not, so they're not uncommon, but things that cause impacts, you know, then if that's not common, basically.
Oh, this is a good question. I'm curious as well. So someone asking from the video that you showed, what did you put on the large meteorite to help preserve it?
So it's got some acid on it to try and get rid of the rust. I think that's what's on it currently. Yeah.
Iron oxidizes and creates rust. So any rocks that have iron in them can rust, including these meteorites.
Exactly. Yeah. So it's probably fine for me to touch, but I didn't think I should. So yeah.
Makes sense. Okay. Oh, so there are some people asking in reference to the last event that we had last week. So the Japanese mission that you mentioned, was that the one that landed on its head or landed upside down?
Yeah, that's Hayabusa 2. They put a small rover on the surface of, they basically threw a small rover at the surface and it tumbled and it fell upside down. But but like I said in the talk last week, it managed to flip itself over and was successful in the end. But Hayabusa 2 also successfully did sampling aside to that as well. So they also descended to the surface with with like an arm and like fist bumped the asteroid basically. So.
And so finally, I think the final question. So someone's asked, and I think we've already answered the first bit, is it possible to find space rocks or bits of space rock on Earth? And I think we've established that yes, we can. But could someone, like in the general public, could someone just potentially find some? And if so, where would be the best places to look?
Oh, what a good question. They're rare. I will say meteorites are rare. We don't typically find them on the street in the middle of a city or anything like that. But if you think you have a meteorite, there are a couple of things to do to check. The first is to see if it's magnetic. So if it's fully magnetic, it might be, you remember how I was saying most of the iron that we find on Earth is a byproduct of mining. You might have a mining product if it's fully magnetic, but if it's like a little bit magnetic and there's a bit of a tug from a magnet from it, you know, interesting. The next thing to look at is if the meteorite has like a shiny black outside surface, or if the rock you have is a shiny black outside surface. That's what we call a fusion crust. You get that when the thing is entering the atmosphere and kind of burning up. If your rock has a shiny black crust and is magnetic, in fact, if it has a shiny black crust and is not magnetic also, send a picture to the Natural History Museum and we can advise you further.
Amazing. Because that's what you do, isn't it? That's part of your job.
That's part of my job, is to work out whether what you have is a meteorite. But it's rare. It is very rare. And we generally, there are generally places that we know where meteorites are found. So for example, there are lots of meteorites that are found around the Barringer crater that we were talking about last week. Not so many found in London.
Yeah, brilliant. And did you tell me before the talk you've actually got some little samples there with you?
I do. Very unexciting samples, but I do have some meteorites sitting on my desk at home. So this was a meteorite that fell in Indonesia in August of last year. And so I don't know if you can see, very, very small, but this is one of those very primitive asteroids, very dark, a bit like that Ivuna specimen that I had. So, sitting on my desk. I've got bags of the stuff.
Amazing. Okay, so on that note, I think we will wrap things up there. So thank you so much, Helena, for joining us. today. That was such a fantastic talk, and I don't think I've ever been more excited about space rocks.
I'm glad.
And thank you all at home for joining us and for engaging with so many fantastic questions. I'm sorry we couldn't get to all of them. So thank you very much. Bye.
Bye, everyone.